As you get farther away from the sun, the temperature goes up. Now this is counterintuitive. It's like if you're trying to heat a marshmallow on a fire, you put the marshmallow closer to the fire to heat it up, not pull it farther away. This has been a mystery for quite a while. According to the nanoflare heating theory of the solar corona, there are very many low-energy nanoflare heating events. Energy is released in a nanoflare. It heats the local plasma to a very high temperature, around 10 million degrees, and there's such a small amount of this very hot plasma that we can't see the individual nanoflares. But as you cool down through the 2 million degree range, which happens fairly quickly, and as many of these events occur, we end up seeing the 2 million degree solar corona that we're used to. One of the objectives of the EUNIS flight was to address this. EUNIS is an acronym for the Extreme Ultraviolet Normal Incidence Spectrograph. It's an instrument that we fly on a sounding rocket out of White Sands Missile Range, New Mexico. It reaches an altitude of about 320 kilometers, which is about 200 miles. We record about 6 minutes of observations of the sun, and then the instrument parachutes back down into the desert where we can retrieve it. Basically, it's two separate instruments, two spectrometers pointed in the same area of the sun, so that we can be observing a very wide wavelength range. Each of these channels is very rich in emission lines. There are many lines from many different ionization stages of lots of different elements. For the purposes of this work, we're interested in the iron-19 and the iron-12 emission. We can see faint emission at those temperatures that provide the further smoking gun evidence for the nanoflare heating theory. So this is very exciting for astronomers and people who are trying to diagnose what's going on in the sun's atmosphere.